In this video, we're looking at example 4 in section 8.5 on Taylor series and Taylor polynomials. In this example, we're going to refer to the Taylor series for the function f of x equals ln of x from example 2 on page 115 above. So we're going to go back and reference that example in a moment. So let's just look at part A. What are we being asked to do? So it says find the maximum errors for your estimates of the ln of 1.05 using P1, P2, and P3. So this is going to be the same procedure, same approach as in example 3, but we're now just looking at a different function and different Taylor polynomials that we created. So to get started though, I want to rewrite that maximum error formula so that we don't have to keep flipping back in our pages. So I'm going to write that out here. So feel free to write it on your page too, so you can refer to it. And then since we're going to be using our work from example 2, let's go ahead and refer back to what we did there. So I just scrolled up to that example. So recall what we did was we found the first, second, and third degree Taylor polynomials centered at 1 for the function ln of 1.05. So what's going to be helpful is for us to refer to this information that we found in this example. So what I'm going to do is go ahead and rewrite some of that information in a table under example 4. So it'll be helpful for us. So the kind of table I'm going to make, I want to refer to the n that I'm using. I want to look at the Taylor polynomial for n evaluated at 1.5. And then in this problem, we're computing maximum errors. So we're going to put that in our final column, maximum error. So we can go ahead and fill in this table. So we saw, we were looking at n equals 1, 2, and 3. We saw that Pn, or P1 of 1.5 was 0.05. So I'm just copying from that example. Feel free to go back and look at your own work here. And then our final piece of 3 of 1.5, we got 0.0487917. All right, so our goal here is to compute this maximum error for each of these Taylor approximations. So let's start with our reminders that will include values that we need in order to write out this maximum error. So we need an A, a C, and then we're going to need to find our M's. So let's write down. So A, our Taylor polynomials were centered at 1. The C value we're looking at here is 1.05. So now when we create these error approximations, the M that we find is going to be found, the M that we're using is going to be found or computed using the n plus 1 derivative of our function. So we're going all the way from n plus 1, n plus 1. We need at least to find the derivative of our function, f of x, to the fourth derivative. So let's go ahead and write those out. So f of x is equal to ln of x. So that would mean the first derivative is equal to x to the negative 1. The second derivative is equal to negative x to the negative 2. The third derivative, and actually we computed this in the previous example. So that is just 2x to the negative 3. The third derivative, and then the fourth derivative is going to be negative 6x to the negative 4. So now we have down all of the derivatives that we will need. So these will come in handy later. All right, so let's get started by looking at when n equals 1 and computing the maximum error of our first degree polynomial. Okay, so for that, we need to find the m. So we need to look at the nth plus 1, so the 1 plus 1, so the second derivative of x, which if we look at those derivatives we just computed, is equal to absolute value of negative 1 over x squared, which, taking absolute value, is just 1 over x squared, because that derivative, the denominator, is always positive. So we need to find an m that's going to be a maximum of this function on the interval from 0 to 1. And not 0 to 1, I misspoke, from 1 to 1.05. So again, we're looking at from A to C. So let's think about what this function does, 1 over x squared. Where is this function maximum or have its largest value on the interval from 1 to 1.05? Well, what's going on here is that we're squaring that denominator. Notice that our values from 1 to 1.05 are all 1 or larger. So when we square it, we're actually going to get a larger number. So this denominator gets larger as we input a larger number on this interval. So we can even write that interval out, right? From 1 to 1.05. We can even graph our function. But since the denominator gets larger here, as we input larger values of x, the maximum value of our function is going to occur at 1. Again, because as we get larger here, our denominator gets larger, which means our fraction, 1 over that larger number, gets smaller. And feel free to graph this if you want to check. But so the max occurs at x equals 1. So what we can do, so if we're looking at 1 over x squared, that is equal to, or rather when we look at the maximum, since the maximum occurs at x equals 1, we can see that this m value will be equal to the value at x equals 1, which is just 1. So m is going to be equal to 1 for us in this case. So let's go ahead and write out that error of the first degree polynomial. So that's going to be less than 1, our m, times 1.05 minus 1. I'll clean this up a little bit so we have some more room. Absolute value of 1.05 minus 1. Okay. Then we're going to raise that to the second power divided by 2 factorial. So we can go ahead and just compute that out. Not too tricky. We can also consult our calculator. We get something around 0.00125. So it's going to be the max error for P of 1. So we're not computing exactly how much of an error we're making, but we're computing a maximum for it. So we know that the error won't be any larger than 0.00125. So let's fill that into our table. 0.00125. All right, so now let's go ahead and do this again with n equals 2 and 3. I encourage you to pause the video and work out these errors, maximum errors, on your own, and then you can come back and compare your work. By working it out on your own, you can then be confronted with where the questions or unknowns are in your calculations. Okay, so let's continue here. So when n equals 2, we need to look at the third derivative of x, which from our work previously, we see that the third derivative is equal to the absolute value of 2 over x cubed. So we need to find the maximum of this function. We need to find the max on 1 to 1.05. And as we see, this function that we have here, 2 divided by x cubed on this interval from 1 to 1.05, that denominator is always positive. So we actually don't even need those absolute values. But we have the same reasoning that we saw when n equals 1. So this function is just going to get smaller as we get larger values of x. Again, because these values that we're using are 1 or larger, every time we cube that number, we're going to get an even larger number. So I'm going to write that down. So here, max occurs at x equals 1. So then we see that 2 over x cubed is going to be less than or equal to 2 over 1 cubed. Again, looking at when x equals 1. So that's just 2. So here M is equal to 2. All right, so now let's go ahead and compute that maximum error. So E sub 2 will be less than or equal to 2 times 1.05 minus 1, now cubed, over 3 factorial, which is going to be equal to 0.000040417. So here's our max error. All right, so now we can go ahead and plug that in above. And I'll just highlight here so we can keep track of our work. So now looking at our table, we're going to fill in the maximum error for P2. 0.1234417. All right. Awesome. So now we just have one more to do. And at this point, we're probably becoming pros at this. So now we're looking at n equals 3. So we need to look at the fourth derivative of f of x. So what did we compute for the fourth derivative? That was negative 6 over x to the fourth. Which is just equal to 6 over x to the fourth. So we need to find the maximum there. On the interval from 1 to 1.05. So same reasoning still applies. This denominator gets even larger as we increase our values of x on the interval from 1 to 1.05. So the max occurs again at 1. So we see that 6 over x to the fourth is going to be less than or equal to 6 over 1 to the fourth, which is just 6. So m for us is equal to 6. So we can just finish off by computing that maximum error. So we can write out our formula. E sub 3 is less than or equal to 6 times 1.05 minus 1 to the fourth over 4 factorial. So using our calculator, we can compute all that out. We get 0.000000, 5 zeros this time, 16. So here's our max error of our third degree polynomial. All right, so let's go ahead and fill that into our table. So up here, we can fill in that our max error for P3 is 0.1234516, 5 zeros. So let's just take a moment to pause and observe what's happening with this error as n gets larger. So not surprising, as we increase our n, the errors that we see here get smaller and smaller. In fact, even using P sub 3, evaluating our function at 0.05 gets us pretty close to our actual function value. Awesome. Great work, everyone. And I hope you noticed I made a little typo here. Didn't affect anything. We used 1.05 throughout our work. But if you want to update that just so that your table is accurate. Awesome. All right. Nice job, everyone.